Okay, guys, we're looking at two sample proportion inferences. More inferences, all the time. So nothing super new here except for the formulas changed just a little bit. So I know you guys have Khan Academy videos and that you're going to be watching those, but I thought I'd give you a real quick kind of rundown on what you're going to be working on. You're starting with proportions, I think I remember that correctly. So I'm going to kind of walk you through a lesson. I'll post this so that you have access to it besides just this video. And I hope this is helpful. I know you don't have a calculator, Inspire calculator at home. I'm going to be looking for that and posting it later, like maybe some online version or something. Okay. All right, so let's look at this. I'm going to go to presentation, and you won't see my lovely face anymore. Okay, so we're looking at two sample proportion inferences. We know what an inference is. We want to be able to draw a conclusion based on information given to us. So we start with our conditions, the things that must be true. And of course, we must have two independent simple random samples from populations or randomly assigned treatments. Okay, our populations, if we have two, still have to be at least 10 times n, but also at the same time, you might have only one population with two treatments. So keep that in mind as well. That's why that population has an S in pink, because it won't always be two. You still need a normal approximation. We get to fudge a little bit here. So instead of 10, now we're going to say 5 if there are two populations, okay? For both the first sample and the second sample, or second population and second population. When we want to do a critical value, When we want to do a confidence interval for our proportions, when we have two proportions, this is what our formula looks like. We have the difference of proportions plus or minus our z star, and then look at that standard error. You can find it on the formula sheet, which I have pulled up. So you can see right here for our p hat, this one population, this is two populations. There is your random variable, your mean, and here's your standard error. Okay, and we are going to be talking about when the two proportions are assumed to be the same and what's called pooling. Okay, so this is kind of referencing right here on your formula sheet. Okay, back to my lesson. Whoop. Okay, so we said statistic, critical value, standard deviation of the statistic. If P is not known, we use P hat. We've talked about that before. Remember, this is also called a standard error. And then Z star times the standard error is called the margin of error. Okay, so kind of just refreshing you on some vocab. So first example, at Community Hospital, the Burn Center is experimenting with a new plasma compress treatment. A random sample of 316 patients with minor burns received the plasma compress treatment. Of these patients, it was found that 259 had no visible scars after treatment. Another random sample of 419 patients with minor burns received no plasma compress treatment. For this group, it was found that 94 had no visible scars after treatment. What is the shape and standard error of the sampling distribution of the difference in the proportions of people with visible scars? Okay, so checking conditions really quick. When we run through, we do have information that is approximately normal. Remember, if we're going to use formulas like standard error formulas, we have to have a normal or approximately normal distribution. Okay, so then it's really easy. And this, in case you're wondering, this 0.82 is coming from our, let me back that up, is coming from our 259 out of 316. Oops, sorry. Going the wrong direction, guys. I am so sorry. There we go. Well, heck, we're just going to go here then. That's from that first group, and this is from that second group. Notice your N is changing based on the group, okay? So, here. This is absurd. There we go. That 0.22 right there, that's coming from your 94 out of your 419. So that's the proportion out of 419. That's the proportion out of 316. And this, of course, is 1 minus p, giving you a standard error of 0.0296. So here's your shape. It is approximately normal. Here's your standard error, 0.0296. Okay. If we want to determine a confidence interval for that, then we do P1 minus P2, then your Z star. Now let's remember what we're looking for here. 95% confidence interval of the difference in proportions, okay? So 95% Z star is 1.96. We've talked a ton about that. Standard error, kind of straightforward here. Here is our interval, 0.537 and 0.654. And if we want to explain what this means, then we would say we are 95% confident that the true difference, I did not word this. We are 95% confident that the difference, that doesn't make sense. The true difference in proportions of people who had no visible scars between the plasma compress treatment and control group is 53.7% and 65.4%. Okay. A second example here, it says, suppose that researchers want to estimate the difference in proportions of people who are against the death penalty in Texas and in California. If the two sample sizes are the same, what size sample is needed to be within 2% of the true difference at a 90% confidence interval? So 2% difference would be 0.02. This is our Z star for 90%. And so as we're going through this, we don't know the proportion. We're not given the proportion, so we use that safe 0.5 proportion. It does say the two sample sizes are the same, which means I can just add them together. And then when I solve this, I would divide by 1.6 square, and then I can cross multiply to get 3383. Okay. Researchers comparing the effectiveness of two pain medications randomly selected a group of patients who had been complaining of a certain kind of joint pain. They randomly divided these people into two groups and then administered the painkillers. Of the 112 people in the group who received medication A, 84 said this pain reliever was effective. So 84 out of 112 believed medication A was effective. Of the 108 people in the other group, 66 reported the pain reliever was effective. So that would be 66 out of 108. It says construct a separate 95% confidence interval for the proportion of people who reported for pain relief, each pain reliever. Based on these intervals, how do the proportions of the people who reported pain relief with medication A or medication B compare? And then it tells you to construct a 95% confidence interval for the difference of the proportions. So this one you're doing two separate intervals, and this one you're doing one interval for the difference. Okay, so if now would be a good time to pause to check to see if you actually understand how to make the intervals, or you can just keep on going with me. Okay, so if I make interval 1, it looks like this. Interval 2 looks like this. Because there is overlap in the intervals, then we would say that there seems to be no difference in the proportion of people who reported the pain relief between the medications because of the overlap. Because there are some that could fall in both, right? And then if I make one big interval, it looks like this. And because 0 is not in the interval, there is a difference in the proportion of people who believe that one would relieve over the other, okay? So 0, of course, being no difference. And if 0, no difference is in our interval, then we would question it. So which one's right? This guy or this guy, right? Who's right? So it kind of depends on how your hypothesis statement is written. So you can write your hypothesis statement 2 ways. The difference of proportions is 0. The difference of proportions is greater than 0 for the alternate, or less than 0 for the alternate, or not equal to 0 for the alternate. Or you could have written your null hypothesis as your proportions are equal, and then you would have one proportion larger, one proportion less, or the proportions not equal. So we have to be sure to define, and then everything will be based on how we define, okay? Now, if our population proportions are equal in the null hypothesis, so if, oh, it's happened again. Oh dear. If we say our proportions are equal in the null hypothesis, we can what's called pool for our variance, and that's where I was showing you on the formula sheet. But you can just look and see on the formula sheet, this is, let me show you one more time. Here we go. When P1 is equal to P2 is assumed, we can find our standard error this way, okay? All right, moving on to our z-score. Our z-score for the difference in proportions looks like this. And of course, it's statistic minus parameter over standard deviation of statistic. And so this guy right here, assuming they're the same, means it's going to be 0. So we don't actually worry about this in this formula because it's assumed 0, okay? So a forest in Oregon has an infestation of spruce moths. In an effort to control the moth, one area has been regularly sprayed from airplanes. In this area, a random sample of 495 spruce trees showed 81 killed moths. 81 had been killed by moths. A second nearby area receives no treatment. In this area, a random sample of 518 spruce trees showed 92 had been killed by moths. Do these data indicate that the proportion of spruce trees killed by the moth is different for these areas? Okay. So we check to make sure that we're good to go. We write some hypotheses saying that P1 is equal to P2, where P1 is the true proportion of trees killed by moths in the treated area versus P2 being the true proportion of trees in the untreated area. And we're saying that there's no difference. Spraying them didn't help, meaning the proportion's the same. And our alternate hypothesis is our spraying worked, and so they're not the same. So we get a z-score, right? And remember, we're just forgetting this whole part that's minus 0 over here, and we're subtracting our proportions over our standard error, and we end up with negative 0.59. Please remember this is a z-score. This is not our p-value, so we do need to either go to our table or to our calculator to find a p-value of 55%, which we would kind of expect because this is really close to 0. Not really close, but pretty close to 0 if you're thinking about how the curve works. And so you end up a lot of area. And if our alpha level is 0.05, 55% is definitely larger than 5%. Okay, so what does our proper conclusion look like in this case? Well, we certainly don't have enough evidence to reject the mean, or the null. So we would say, assuming the null hypothesis is true, that the proportion of trees killed by moths is the same in the treated and the non-treated areas, there is a 0.55 probability of getting a difference in proportions of 0.02 or more extreme purely by chance. This is weak evidence against the null hypothesis and not significant at 0.05. I fail to reject the null. There is not sufficient evidence to suggest that the proportion of spruce trees killed by moths is different. So exact same that we've been doing, formulas just change a little bit. Okay, I hope this helps. Good luck on your Khan Academy. Message me or email me and let me know if you have any questions, and I will try to help.